Hi everyone, this is Santhosh Kumar from Sims Academy. Today we are going to do some numericals based on the work done by a variable force. Okay, let us see the first numerical over here. A variable force given by the two-dimensional vector f equals to 3x square I plus 4j acts on a particle. The force is in Newton and x is in meter. What is the change in the kinetic energy of the particle as it moves from the point with coordinates 2, 3 to 3, 0? The coordinates are in meters. Okay. As we know, according to work energy theorem, we have the work done on an object is equal to change in kinetic energy. Okay. Here the force is given in terms of vector form, vector notation. F equals to 3x square I plus 4j. Now, if we consider a small work done, dw equals to, we write it as F into dx. If you want to find out the complete work done, then we integrate, that is integral F into dx. As the coordinates are being given here, x coordinate, that means it is going from 2 to 3, and in y direction it is moving from 3 to 0. Okay. Now what is f given over here? Integral 3x square I into dx. Let us integrate x differently and y term differently. Here in the x coordinates, the limits are from 2 to 3, and in the y coordinates we have from 3 to 0. It is 4j into dx. Even we need not, when we are integrating separately, we need not consider this I and j here. Okay, 3x into dx and 4 into dx. As we know the formula of integration, integral 1 into dx, it is x, and integral 3x square, that is x square dx equals to x cube by 3. Here we have work done equals to integral 2 to 3. 3 we can keep it outside because it is the constant, and here x square dx plus integral 3 to 0, 4 we can keep it outside, it is 1 into dx, that equals to 3 into x cube by 3 under the limits 2 to 3 plus 4 into integral 1 dx, it is x under the limits 3 to 0. Okay, that equals to, this 3 gets cancelled, x cube under the limits in the sense upper limit 3 cube minus lower limit, it is 2 cube, plus 4 into upper limit, it is 0, minus 4 into lower limit, it is 3. Hence we get it as 27 minus 8 minus 12, that equals to 27 minus 20, which equals to 7 joules. Hence, we got the work done as 7 joules. Work done is nothing but the change in kinetic energy, which equals to 7 joules. Here is our option. I hope you understood. This is the integration we have done over here. Let us move on to the next numerical. When a spring is stretched by 2 centimeters, it stores 100 joules of energy. If it is stretched further by further 2 centimeters, the stored energy will be increased by. Okay, here, what is the potential energy that is stored by the spring? We have half k x square, where k is the spring constant and x is a elongation. Or if we want to write in terms of force and elongation of fx, or if you want to write in terms of force and spring constant, that is f square by 2k. We need to take the formula which is appropriate for the given problem. Okay, here we are given a spring is stretched by 2 centimeters. It stores 100 joules of energy. If it is further stretched by 2 centimeters, that means the spring is same, in the sense spring constant remains same, and there is a difference in elongation. Initial elongation, here we have x1 equals to 2 centimeters, and let us say potential energy initial even as 100 joules. And we need to find the value of E2, where x2 is given as further it is stretched by 2 centimeters, in the sense 2 plus 2, that is 4 centimeters. Now, from this formula, half and k both are constants. Hence, we can write E is proportional to x square, or E2 by E1 equals to x2 square by x1 square, which implies E2 by E1 we have here it as 100 joules, x2 square it is 4 square by x1 square it is 2 square, which implies E2 by 100 equals to 16 by 4, which is 4. Implies E2 equals to, we have 4 into 100, that is 400 joules. That means if you answer 400 joules here, you see there, you can observe 400 joules is not the correct answer. We need to check out the question once again. If it is stretched further by 2 centimeters, the stored energy will be increased by. Increase is said. How much is initial? 100. How much is final? 400. Then the increase in energy, let us say it as delta E equals to E2 minus E1, that is 400 joules minus 100 joules, which equals to 300 joules. You can observe here, we have two options, 300 joules and also 400 joules. That's why we need to read the question carefully and we should move on further. Okay, let us move on to the next problem. Okay, the same type of question is being given again. A spring is stretched by 2 millimeters. Its potential energy becomes 4 joules. Okay, x1, let us take it as 2 millimeters, and potential energy, let us say it as E1 equals to 4 joules. And in the second case, it is stretched by 10 millimeters. As we are considering the ratio, we need not change it millimeters into meters. We should find, in this problem, we need to find the final, its potential energy equals to. He did not ask us to find the difference in or the increase in potential energy, the total, the final potential energy. As I have told you, the potential energy E equals to half k x square. The same spring has used in the sense K remains constant, 1 by 2 is also constant, hence E is proportional to x square or E2 by E1 equals to x2 square by x1 square, implies E2 by E1 we have it as 4 equals to x2 square 10 square by x1 square 2 square, implies E2 by 4 equals to 100 by 2 square anyway 4 4 and here we need to check out if it is stretched by 10 millimeters its potential energy is equals to uh, 10 square okay 4 x1 square 2 square, it is 100 by 4. Yeah, we are getting 25. That means E2 equals to 25 joules. Our option is none. Okay, let us move on to the next numerical here. A particle with total energy is total energy with E is moving in a potential energy regions U of x. Motion of the particle is restricted to the region when. Okay, now let us consider a spring in which we are applying some force with some total energy, whatever it is given as E. If suppose if the total energy E which we are applying is greater than the potential energy of the spring, then obviously the spring breaks. That means whatever the energy we apply, the total energy we apply, that must be less than the potential energy of the spring. Less than the potential energy of the spring in the sense the potential energy of the spring should be greater than the total energy. Okay, this is the spring. Let us suppose, yes, its potential energy is U. We are applying the energy, sorry, some force, where due to that force, the energy we are applying is E. If E is greater than this potential energy U of x, whatever he has said, then the spring breaks. Hence, the motion of the particle is restricted to the region when that restriction is done only when this U of x is greater than E. As I told you, E must be less than U of x. Let us move on to the next numerical. Again, we have a particle moves in a straight line with retardation proportional to its displacement. Its loss of kinetic energy for any displacement x is proportional to. Retardation is proportional to its displacement. That means acceleration is proportional to displacement but in opposite direction. When is this possible? The acceleration is proportional to displacement but in opposite direction is possible in case of SHM, that is simple harmonic motion. Even in case of simple harmonic motion, the work done according to this one, according to work energy theorem, we have the work done is equals to the change in kinetic energy, which equals to half k x square. Here it is minus x, okay? That is half k. In this particular case, we are saying k equals to half k into minus x whole square. That equals to half k into x square again, where k is constant, half is constant. Hence, the loss in kinetic energy is proportional to the square of the displacement. Hence, our option is A. Let us move on to the next numerical here. If we throw a body upwards with velocity of 4 meters per second, okay, at what height does its kinetic energy reduce to half of the initial value? Now we need to think about the law of conservation of energy. Okay, let us say this point is A. This one is B, and this position, let us say C. Initially, whenever the bond is thrown vertically upwards with some velocity of 4 meters per second, here, as it is on the surface, its potential energy is zero, but there is some kinetic energy. At the maximum height, as the velocity of the object is zero, we have kinetic energy as zero, but the object only possesses potential energy. Whatever might be the energy that is present, the total energy of the system always remain constant according to the law of conservation of energy. At this particular point B, let us suppose the kinetic energy has become half. In the sense, here we have both potential energy and kinetic energy. Then what about the loss of kinetic energy? How much is the loss in kinetic energy here? Okay, let us find initial kinetic energy first. U equals to 4 meters per second he has given us. Let us consider the mass of the object as he did not give us. Let us take it as m. Then initial kinetic energy equals to half m u square, that equals to half m into u. It is given as 4 square, 4 into 4, 2 ones, 2 twos, that is 8m we got. But at B, the kinetic energy has become half of that. That means 4m. Then what about the remaining energy? The total energy must be 8m. But the kinetic energy has become 4m. That means the remaining energy will be in the form of potential energy, which is equals to that 4m. Now, what is the formula for potential energy? We have mgh equals to 4m. M gets cancelled on both sides, and h equals to 4 by g, as we are asked to take the value of g as 10 meters per second square. It is second square, 4 by 10, that is 0.4 meters. At that height, at a height of 0.4 meters, the kinetic energy has become half of the initial value, and whatever the loss in kinetic energy, that is converted into potential energy. And here is our option, that is 0.4 meters. I hope you got the clarity regarding this. We shall go on to the next question. If a long string, I think it is spring, okay, whatever it might be. If a long spring is stretched by 0.02 meters, its potential energy is U. If the spring is stretched by 0.1 meter, then its potential energy will be. Here also the same thing, the potential energy E equals to half kx square, as he has taken the same spring, and the displacement, that means the stretch of the spring, is given, elongation. Now k is constant, half is constant, E proportional to x square. Here E1 equals to, has given it as U, E2 we need to find out, and x1 equals to 0.02 meters, and x2 equals to 0.1 meter. Then as E is proportional to x square, we can take E2 by E1 equals to x2 square by x1 square, which implies E2 by E1 he has given is as U x2 square 0.1 whole square, 0.1 into 0.1 by x1 square, it is 0.02 into 0.02. Okay, here if you cancel this point, both the points or the decimals will be gone. Finally, we'll get the value as 1 by 2 to 4, that is 0.04. If we cancel, we can multiply 100. That means 100 by 4, which is 25. That means we got the value E2 by U equals to 25, which implies the final potential energy, or the potential energy when the spring is stretched by 0.1 meter is 25 U. And here is our answer. Okay, let us move on to the next one. A uniform chain of length 2 meters is kept on a table such that a length of 60 centimeters hangs freely from the edge of the table. The total mass of the chain is 4 kg. What is the work done in pulling the entire chain on the table? Okay, let us draw the diagram related to that numerical. This is a table, let us suppose. Yes, and this is the chain which is hanging. Okay, if 1 by nth of the chain is hanging, then work done W equals to mgl by 2n square. Here we are given the value of m equals to 4 kg, and L The length of the chain, it is 2 meters. And G value, okay, let us take it later. And how much is hanging? 60 centimeters. That means 1 by n equals to 60 centimeters by the total one is 2 meters, in the sense it is 200 centimeters. 0 gets cancelled, 2 threes, 2 tens, implies we got 1 by n equals to 3 by 10. By doing the invertendo, we get n value as 10 by 3. Let us substitute the value of n in the given formula, as the options are quite, the difference between the options is quite larger. Let us take the value of G as 10 meters per second square only. Hence, the work done W equals to mgl. 4 into G is 10 into L, we have 2 meters by 2n square, that is 10 by 3 into 10 by 3. 10 gets cancelled, 2 and 2 also gets cancelled. Finally, 4 into these 2 threes goes upward by 10. 3 threes 9, 9 fours 36 by 10. That is the work done in pulling the chain onto the table is 3.6 joules. Here is our option P. Hope you understood this. In this particular problem, finding the value of n is very important. The formula is given as whenever 1 by nth chain of nth part of the chain is hanging, then the formula is given as W equals to mgl by 2n square. Here the fraction of the chain that is hanging, we found out 1 by n equals to 60 centimeters by the length is given in terms of meters, hence I converted that into centimeters, 200 centimeters. We got the value of n as 10 by 3, and finally W equals to mgl by 2n square, which equals to 3.6 joules. Next numerical. Okay. The potential energy of a body is given by U equals to A minus BX square. The magnitude of the force acting on the particle is constant, proportional to x, proportional to x square, inversely proportional to x. Okay, let us see. Actually, we write generally the small work done dW equals to F into dx. That means the small potential energy du equals to F into dx, or by sending the dx to this side, we get F equals to d by dx of u. Here we are given the value of u as A minus bx square. Let us write the formula of differentiation. D by dx of constant equals to 0. D by dx of x equals to 1. And d by dx of x square equals to 2x. These are the formulae related to our differentiation in mathematics. Here, f equals to d by dx of u a minus bx square. F equals to d by dx of a minus, let us keep b outside, b into d by dx of x square, which implies f equals to d by dx of constant, it is 0, minus b into d by dx of x square. As I told you previously, it is 2x. Hence, we get the value of f as minus 2bx. Here, 2 and b are constant. Hence, the force is proportional to x, that is displacement. Here you see the small work dW, we always take it as F into dx. The work is nothing but work done is converted into energy by using that potential energy only. Du equals to F into dx, or by rearranging, we got the value of F as d by dx of u, that is du by dx. U value is given a minus bx square. D by dx of a, that is constant, is 0, minus b into d by dx of x square, it is 2x. Hence, finally we obtain the value of F, that is the magnitude of force, as minus 2bx. As 2 and b both are constants, F is proportional to x. That means force is proportional to displacement. Okay, we shall move on to the next question. Okay, small question. Here, which of the following is not a conservative force? What are conservative and non-conservative forces? Generally, we say all the field forces or forces at a distance are conservative forces. What are the field forces? We have gravitational, force, electrostatic force, and even magnetic force. All these come under the conservative forces, but we have what are non-conservative forces? Generally, non-conservative forces are frictional force, because these conservative forces, they do not depend upon the path which the object is moving. But these non-conservative forces, they depend upon the path in which the object is moving. Suppose I'm moving, I'm riding a car. For about 1 kilometer, I went on a very smooth road. And for another kilometer, I went on a very rough road, ghat road or very rough road, let us say. On the smooth road, the friction is less, but on the rough road, the friction is more. That means in which path we are moving, that force that is affected by the frictional force. Hence, these forces depend on the path. Then frictional force, we can even consider viscous force, and viscous force in case of liquids, and the same viscous force in case of gases, we say it as drag, etc., are non-conservative forces. Hence, what is the option in our question? Which one of the following is not a conservative force? That is frictional force. Here we have done with the 10 questions from the chapter of work, energy, and power. And here, later, in the next session, we are going to deal with some more numericals from the same chapter. And this is Santhosh Kumar from Sims Academy, signing off. Take care.